In previous group theory lecture, we see that if G is abelian, then all its subgroup of group G are normal, but its converse is not true, with the example of group of quaternion. Now we see the next example. If n and m are the normal subgroup of group G, then n into m is also normal subgroup of group G. Let us see the proof of that example. फर्स्ट शो दॅट एन एम इज सबग्रुप ऑफ ग्रुपची. सबग्रुपचा क्रायटेरिया काय आहे, दोन इलेमेंट सबग्रुपमध्ये असतील तर सपोज एक्स वाय बिलॉंग्स टू दॅट सबसेट एच अँड इफ एक्स इन टू वाय इनवर्स असं बिलॉंग्स टू एच देन एच इज सबग्रुप. मग एन एम हा सबग्रुप आहे म्हणजे एन एममधले दोन इलेमेंट घ्यायच्यात तुम्हाला आणि त्यांचा इनवर्स म्हणजे पण त्या एन एममध्ये असला पाहिजे. प्रोडक्ट ऑफ एक्स इंटू वाय इनवर्स ऑल्सो बिलॉंग्स टू एन एम. आपण दोन इलेमेंट घेऊया. एन एम हा सेट कसा असणार आहे की एन मधला इलेमेंट एक एम मधला इलेमेंट कॉल्ड स्मॉल एन अँड एम. नाव टेकिंग टू इलेमेंट्स एक्स it is n1 m1, y is n2 m2, where n1 n2 belongs to n, m1 m2 belongs to m. Then x into y inverse is equals to n1 m1 into n2 m2 inverse, which is equals to n1 m1 into m2 inverse n2. कारण a into b inverse कसं लिहितो आपण, b inverse a inverse, म्हणून आपण n2 m2 inverse कसं लिहिणार आहे, m2 inverse n2 inverse. मग आता m इंटू m2 इनवर्स हा काय एम मधला इलेमेंट आहे. एम हा काय सबग्रुप आहे ग्रुप जीचा. मग आपण त्याला काय म्हणूया, m3 म्हणूया. मग हा कसा आला n1 m3 n2 इनवर्स. नाव अगेन e इज आयडेंटिटी, वी प्लेस e in between n1 m3. therefore we have x into y inverse is equals to identity substituting by n2 inverse n2. It is an adjustment. Therefore we have by associative property, this is n1 n2 inverse n2 m3 n2 inverse by associative law. But n1 n2 inverse belongs to n since n is subgroup, and n2 m2 n2 inverse belongs to m since m is normal subgroup of group G. Therefore we have the element n3, it is an element of n, and m4 it is element of m. Therefore n3 into m4 belongs to nm. Then by sufficient condition of subgroup, nm is subgroup of group G. Now to show that nm is normal in group G, for that purpose we have to show that G inverse xg belongs to nm for every G belongs to G and x belongs to nm. x हा nm मधला इलेमेंट म्हणजे n मधला एक इलेमेंट m मधला एक इलेमेंट. therefore can be written as x equals to n into m, where n belongs to n, m belongs to m, g belongs to g with the arbitrary element. Then g x g inverse, which is equals to g nm g inverse. Write down the identity e, that is g n e m g inverse, since e is identity, which is equals to g n identity can be substituted as g inverse g, g n g inverse, g m g inverse. And this is n is normal subgroup, m is also normal subgroup. Therefore gn g inverse belongs to n, gm g inverse belongs to m. Hence gn g inverse into gm g inverse belongs to nm. This proves that nm is normal subgroup of group G. That is, we prove that product of two normal subgroup is again normal subgroup. What about the other condition, that is normality criteria means, that is product of two subgroup, it is need not be an subgroup. For example, if in group S3 h equals to rho naught mu 1, k equals to rho naught mu 2, then h into k, it is rho naught into rho naught into mu 2, mu 1 into rho naught mu 1 mu 2. But here the element rho naught mu 2 mu 1 rho 2, it is an element of hk. For proving that it is the subset is subgroup, we have to prove that an element and its inverse also belongs to that subset. But here we observe that rho 2 belongs to hk, but rho 2 inverse is rho 1 in S3, which is not in the product hk. Therefore hk is not a subgroup of S3. That is, we prove that the product of two subgroup need not be subgroup. Next we see the example. If n is normal subgroup of group G and h is any subgroup of group G, then h into n is subgroup of group G. Here we above prove that product of two subgroup need not be subgroup, but one of the subgroup is normal, then product of that subgroup is again subgroup of group G. Here we prove the example. Now here we prove that Nm is a subgroup of group G. That is, on the same way NH is also subgroup of group G. Now prove the condition and the corresponding criteria. Here we have to prove that Nm equals to Mn for every n belongs to n if and only Nm into Mn inverse, it is identity. If and only if Nm into n inverse M inverse equals to identity. That is, we have to show that Nm into n inverse M inverse, it is an identity. कारण हा कशामध्ये असणार आहे, हा एन मध्ये पण असणार आहे आणि एम मध्ये पण असणार आहे, म्हणजे त्यांच्या इंटरसेक्शनमध्ये असणार आहे. हे आपल्याला प्रूव्ह करायचं आहे. चला, आता एन एम इंटू एन इन्वर्स एम इन्वर्स काय आला पाहिजे, आयडेंटिटी आला पाहिजे, आपलं क्लेम आहे. नाव टू प्रूव्ह दॅट एन एम एन इन्वर्स बाय असोसिएटिव्ह लॉ. Now the Nm n inverse belongs to M. Since M is normal subgroup, call it as M1. Therefore M1 M inverse it belongs to M, called as M2. Therefore Nm n inverse M inverse belongs to M. Also here we observe that Nm n inverse M inverse also can be written as associative by associative law, n into M n inverse M inverse. Since n is normal subgroup, it belongs to N, called as N1. It is N1 N2 belongs to N, called as N2. Here we observe that Nm n inverse M inverse both belongs to M and N, hence it belongs to N intersection M. But N intersection M is identity. Therefore Nm n inverse M inverse equals to identity. Hence our claim is proved that is Nm is equals to Mn for every n belongs to N, for every M belongs to M. Hence we prove the result, that is, if n is normal subgroup of group G and H is any subgroup, then Hn is also subgroup of group G.